Okay, in this video I'm going to talk about the Bevan point of a triangle. So let's say that we have an arbitrary triangle and we consider the excircles of this triangle. So basically the circles that are tangent to one of the sides and the extensions of two other sides. So this circle, there is not enough place to draw the full circle, but and this circle. Yeah, so it's and we consider the tangency points and the centers of the circle, of the circles. So this, and this. And so this, the lines connecting the centers to the tangency points, they are of course perpendicular to the sides. But the theorem is that these three lines intersect at a single point, and this point is called the Bevan point of the triangle. So let's introduce the points. So ABC is the original triangle. Let the centers be IA prime, IB prime, IC prime, and the tangency points we denote by TB prime, TA prime, TC prime. And the theorem is that I A prime, TA prime, I B prime, T B prime, and I C prime, TC prime intersect at a single point which is called the Bevan point of the triangle ABC. Yeah, so let's prove this. So for the proof, so first we will calculate the angles. So first notice that so the center of the excircle, it lies on the intersection of the bisectors of the angles, so of the internal angle B and of the external angles, this and this, of the external angles A and C. But so the same for this circle. So IA prime lies on the bisector of this angle, of the external angle. But because this is the same angle basically, so these two bisectors, they it's the same line. So basically the points IB prime, C, and IA prime, they lie on the same line, which is the bisector of the external angle. So the same is for this point, which would lie here actually. and the same for the third bisector. So they all lie on the same line. So now we calculate the angles. So let's denote the angles of the original triangle as alpha, beta, and gamma. And so then the external angle for the angle A is 180 minus alpha, and because it's a bisector, because these two angles are equal, so each of them would be 90 degrees minus alpha over 2. Right? So the same as so this angle is the same, alpha over 2, and the same for this angle. This would be 90 degrees minus beta over 2. This also 90 degrees minus beta over 2. And here we have 90 degrees minus gamma over 2 and 90 degrees minus gamma over 2. Right, so now so to calculate, so let's calculate this angle. So this angle is, so like we have a right triangle, right? Because this is perpendicular, the radius of the circle is perpendicular to the tangent. So therefore, so since this is 90 minus gamma over 2, so this is just gamma over 2. Right? So similarly here we have alpha over 2, and for the rest of the angles, so here we have gamma over 2, here we have beta over 2, here we have beta over 2, and here we have alpha over 2. Okay, so we calculated all these angles, and now we notice, that gamma over 2, so we have here gamma over 2 and here gamma over 2. So this triangle, so we don't yet know if they intersect at a single point. So let me remove this and draw it so that they deliberately not intersect at a single point, something like this. So if we consider the intersection point of two of these lines, then basically this IB prime, this point IA prime, this triangle is isosceles because it has two equal angles. So from this we conclude that like this segment, so like if we denote this point temporarily by so let's say P, so this point denoted by P, so then we conclude that IB prime P is equal to P IA prime. Yeah, so and the same holds true for the other lines. So like this segment, this triangle is also isosceles, so this segment is equal to this segment, but it could be a different point, you see. So from this we can roughly it doesn't give us a proof yet, but what we can guess from this construction is that this Bevan point, if these three lines indeed intersect at a single point, this point must be the circumcenter. So the Bevan point must be the circumcenter of the triangle IA prime, IB prime, IC prime. You see, because like if it indeed was a single point of intersection of these three lines, then this would be like equal to P I C prime. So P would be at the same distance from all these 3 points IA, IB, IA prime, IB prime, and IC prime. So this would be the circumcenter, but we don't know yet that. So this is kind of a motivating idea for why we need to consider the circumcircle of this triangle. But like maybe it would be possible to, like, with some additional argument to prove like directly from this equality, but I'm going to use a different argument. So so we know, so we consider the circumcircle. Yeah, circumcircle and the circumcenter. So let's denote it by circumcenter of this triangle denoted by let's say Q is the circumcenter. So we know, like, so there is a theorem about the angles of circumcenter and orthocenter. So like if we have a triangle, we have an altitude, and like here somewhere orthocenter, and we have a circumcenter, then these two angles are equal to each other. So this is the, like, it's a well-known theorem, and I proved it in one of the previous videos. Like, it's just angle calculation, like it's not difficult to prove. But so, like, if we apply it here, so you see in this triangle, this large triangle, so we know the angles of this triangle, and so if we consider the altitude here, so if we consider the altitude, so what would be this angle between the altitude and this side? So this would be simply 90 degrees minus this angle, right? So yeah, so let me draw it separately, this triangle, because there is too much information on this picture. So like we have this triangle, right? So IA prime, IB prime, and IC prime. And so we know this angle, it is beta over 2 plus gamma over 2. So this angle is beta over 2 plus gamma over 2. And now we consider an altitude here. And so this angle would be simply 90 degrees minus this angle. So it would be 90 degrees minus beta over 2 minus gamma over 2. Right? And so if you have a circumcenter Q, the circumcenter of this triangle, then by this theorem, like this angle must be the same. So it should be 90 degrees minus beta over 2 minus gamma over 2. Now let's simplify this. So what is 90 degrees minus beta over 2 minus gamma over 2? We know that alpha plus beta plus gamma, these are the angles of the original triangle. Their sum is 180 degrees, right? So this is basically equal to 180 minus beta minus gamma over 2. So 180 minus beta minus gamma is simply alpha. So this is equal to alpha over 2. So both of these angles are actually equal to alpha over 2. Alpha over 2, alpha over 2. These two angles. Okay. So the angle IC, IB, Q, where Q is the circumcenter of this triangle. So this is alpha over 2. So now if we return to the original picture, we see that we already have an angle alpha over 2 here, right? Angle alpha over 2 is between this side and this line. So the angle AIB prime TB prime, we already calculated this as alpha over 2, and because we just proved that that this angle between this side and the line IB prime Q is also equal to alpha over 2. So this implies that this is simply the same line. So this implies because the angle alpha over 2 is equal to this angle alpha over 2, it means that the point Q, it lies somewhere on this line, like somewhere here. Well, it's not obviously here, but like for now, like all we proved is that it lies on the same line. Yeah, so let's remove it. But the point is that, so what we proved is that Q belongs to the line IB prime TB prime. IB prime TB prime. But a similar argument by calculating angles, we can conclude that it lies on the other two lines as well, because similarly we calculate the angle between Q and this side. And this side we similarly conclude that it would be what it would be. It would be beta over 2. Yeah, so this angle would be beta over 2. And yeah. So this is also alpha over 2, this is beta over 2, and this is like this angle is gamma over 2. So because of this angles, like we see that Q also belongs on this line, because this angle is also beta over 2, and on this line because this angle is beta over 2 and this angle is alpha over 2. So similarly we prove that Q belongs to I A prime T A prime, and Q belongs to I C prime T C prime. So from this it immediately follows so that Q belongs on all of these three lines. It means that these three lines intersect at a single point. So I A prime T A prime, I B prime T B prime, I C prime T C prime intersect at a single point, which is also is also the circumcenter of the triangle A prime, B prime, IC prime. Yeah, and this point is also called the Bevan point of the triangle ABC. So this concludes the proof.